Hi everybody. So I'm going to take the Google Cloud Fundamentals Core Infrastructure course. I'm gonna do a daily studying for this course until I either one pass the Solution Architect certification on Google Cloud Platform, or I land a new job. So let's get to it. Let's get to studying with me together. The goal of this course is to provide you with an overview of Google Cloud. Google Cloud offerings can be Google Cloud offerings can be broadly categorized as compute, storage, big data, machine learning, application services for web, mobile, analytic, and backend solution. Through a combination of videos, quizzes, and hands-on labs, you'll learn the values of Google Cloud and how cloud solutions factor into business strategies. The intended target audience of today's course consists of solution developers, system operations professionals, and solution architects planning to deploy application and create application environment of Google Cloud. The course also used for business decision maker evaluating Google Cloud. While you should be happy to hear that we'll be finding out about services and concepts that are specific to Google Cloud in this course, do keep in mind that as fundamentals level course, some content will be geared toward learners who are entirely new to cloud technologies. I am not totally new to cloud technology. I have in-depth hands-on experience with Google Cloud myself already. But however, I want to go back to the fundamental because I'll be doing interviews. We all know that real world experience doesn't necessarily translate it to the textbook fundamentals, the definition and some terminologies. So that's why I'm exploring this course and try to get the certificates and then do better in interviews. I believe that combine the textbook knowledge with hands-on experience, I'll have a better chance, doing better in interviews and landing the next job. This course has no prerequisites. Although it's helpful, be familiar with application development, Linux operating systems, systems operations, and data analytics, machine learning to best understand the technologies covered. And there are 7 key learning objectives that we are hoping to achieve by the By the end of this course, you should be able to identify the purpose and value of Google Cloud products and services. Define how infrastructure is organized, controlled in Google Cloud. Explain how to create basic infrastructure in Google Cloud. Select and use Google Cloud storage options. Describe the purpose and value of Google Kubernetes engines. Identify the use cases for serverless Google Cloud Service, and combine Google Cloud knowledge with prompt engineering to improve Gemini responses. And then we'll go to the next activities. Let's start beginning with the overview of cloud computing. The cloud is hot topic these days, but what exactly is it? The U.S. Institute and Standard and Technology created the term cloud computing, although there is nothing U.S. specific about it. Cloud computing is a way of using information technology that has these 5 equally important traits. First, customers get computing resources that are on demand and self-service. On demand and self-service. Through a web interface, users get processing power, storage, and network they require without the need of human intervention. Second, customers get access to those resources over the internet from anywhere they have a connection. Third, the cloud provider has a big pool of those resources and allocates them to users out of the pool. That allows the provider to buy in bulk and pass the saving on to the customers. Customers don't have to know to care about the exact physical location of those resources. Fourth, the resources are elastic, which means they are flexible, so customer can be. If customers need more resources, they can get more and quickly. If they need less, they can scale back. And finally, customer pays only for what they use or reserve as they go. If they stop using resources, they stop paying. This is very vital for ongoing exercises. And that's it. That is definition of cloud. But why is the cloud model so compelling nowadays? To understand why, we need to look at some history. The trend toward cloud computing started the first wave known as co-location. Co-location gives users the financial efficiency of renting physical space instead of investing in data center real estate. Virtualized data center of today, which are the second wave, share similarities with the private data centers and co-location facility of decades past. The component of virtualized data center match the physical building blocks of hosted computing, servers, CPUs, disk, load balancer, and so on. But now they are virtual devices. With virtualization, enterprise will maintain the infrastructure, but also remain the user control and user configured environment. Several years ago, Google realized that its business couldn't move fast enough within the confines of the virtualization model. So Google switched to a container-based architecture, a fully automated, elastic, third-wave cloud that consists of a combination of automated services and scalable data. Services automatically provision and configure the infrastructure used to run applications. Today, Google Cloud makes the third-wave cloud available to Google customers. Google believes that in the future, every company, regardless of size of industry, will differentiate themselves from its competitor through technology. Increasingly, that technology will be the form of software. Great software is based on high-quality data. This means that every company is and will eventually become a data company. The move to virtualized data center introduced customer to two new type of offering: infrastructure as a service, commonly referred to IaaS, and platform as a service, or PaaS. IaaS offering provide raw compute, storage, and network capabilities organized virtually into resources that are familiar to physical data center. Compute Engine is an example of Google Cloud IaaS service. PaaS offerings, in contrast, bind code to library that provide access to infrastructure application needs. These allow more resource to be focused on application logic. App Engine is an example of Google Cloud PaaS service. PaaS, platform as a service. Okay, that's why PaaS. App Engine is example of a Google Cloud PaaS service. In the IaaS model, customer pay for the resources they allocate ahead of time. In the PaaS model, customers pay for the resource they actually has. Wait. Let's digest this. In the IaaS, infrastructure as a service model, customers pay for the resources they allocate ahead of time. In the platform as a service model, customers pay for the resources they actually have. No. Pay for what they actually use. Okay. Got it. As cloud computing has evolved, the momentum has shifted toward managed infrastructure and managed services. Leveraging managed resources and services allow companies to concentrate more on their business goal and spend less time and money on creating and maintaining their technical infrastructure. It allows companies to deliver products and services to their customer more quickly and reliably. Serverless is yet another step in evolution of cloud computing. It allows developers to concentrate on their code rather than on server configuration by eliminating the need for any infrastructure management. Serverless technologies offered by Google include Cloud Run, which allow customers to deploy their containerized microservices-based application in a fully managed environment. And Cloud Run functions, which manage event-driven code as a pay-as-you-go service. While it's outside of scope of the course, you might have heard of software as a service, SaaS, and wonder what it is and how it's fit into cloud ecosphere. SaaS provides an entire application stack, delivering an entire cloud-based application to customer can access and use. Software as a service applications are not installed on your local computer. Instead, they run in the cloud as a service and are consumed directly over the internet by end user. Popular Google applications such as Gmail, Docs, Drive that are part of Google Workspace are all examples of that. Let me see this Google Cloud Network. Google Cloud Network, okay. Google Cloud runs on Google's own global network. It's the largest network of its kind, and Google has invested billions of dollars over many years to build it. This network is designed to give customers the highest possible throughput and lowest possible latencies for their applications by leveraging more than 100 content cache nodes worldwide. These are locations where high demand content is cached for quicker access, allowing applications to respond to user requests from the location that will provide the quickest response time. Google Cloud's location underpins all of the important work we do for our customers. For redundant cloud region to high bandwidth connectivity via subsea cables, every aspect of our infrastructure is designed to deliver your services to your users, no matter how they are around the world. Google Cloud's infrastructure is based in 7 major geographic locations: North America, South America, Europe, Africa, and Middle East, Asia, and Australia. So we have North America, South America, Europe, Africa, Middle East, Asia, and South Asia, and Australia, not South Asia. Having multiple service locations is important because choosing where to locate applications affects qualities like availability, durability, and latency, the latter of which measure the time a packet of information takes to travel from its sources to its destination. Each of these locations is divided into several different regions and zones. For example, London, or Euro West 2 is a region that currently comprises 3 different zones. A zone is an area where Google Cloud resources are deployed. For example, if you launch a virtual machine using Compute Engine, it will run in the zone that you specify to ensure resource redundancy. You can run also resources in different regions. This is useful for bringing application closer to users around the world, and also for protection in case there are issues with the entire region, such as natural disaster. Some of Google Cloud services support placing resources in what we call a multi-region. For example, Spanner multi-region configuration allows you to replicate the database data not just in multiple zones, but in multiple zones across multiple regions as defined by the instance configuration. Okay. These additional replicas enable you to read data with low latency from multiple locations close to or within the regions in the configuration, like the Netherlands and Belgium. The number of zones and regions Google Cloud support is increasing all the time. You can find the most up-to-date numbers at cloud.google.com about location. Okay. The virtual world, which includes Google Cloud's network, is built on physical infrastructure, and all those rack of humming servers use huge amount of energy. Altogether, existing data centers use roughly 2% of the world's electricity. With this in mind, Google works to make their data center run as efficiently as possible. Just like our customers, Google is trying to do the right thing for the planet. We understand the Google Cloud customers have environmental goals of their own, and running their workloads on Google Cloud can be part of meeting these goals. Therefore, it's useful to know the Google Cloud Data Center were the first to achieve ISO 14001 certification, which is a standard that maps out framework for an organization to enhance its environmental performance through improving resource efficiency and reducing waste. As an example of how it's being done, here's Google Data Center in Hamina, Finland. The facility is one of the most advanced and efficient data center in Google fleet. Its cooling system, which uses seawater from the Bay of Finland, reduces energy use and is the first of its kind anywhere in the world. In our founding decades, Google became the first major company to be carbon neutral. In our second decade, we were the first company to achieve 100% renewable energy. By 2030, we aim to be the first major company to operate completely carbon-free. Nine of Google's servers has more than 1 billion users each, and so you can be assumed that security is always on the minds of Google's employees. Design for security is prevalent throughout the infrastructure that Google Cloud and Google services run on. Let's talk about a few ways Google works to keep customer data safe. The security infrastructure can be explained in progressive layers, starting from physical security of our data center, continue on to how the hardware and software that underlie the infrastructure are secure, and finally describing the technical constraints and processes in place to support operational security. We begin with the hardware infrastructure layer, which comprises three key security features. The first is hardware design and provenance. Both the server boards and networking equipment in Google Data Center are custom designed by Google. Google also designs custom chips, including a hardware security chip that is currently being deployed on both servers and peripherals. I always suck at pronouncing this word. The next feature is a security book stack. Peripherals. Google server machine uses a variety of technology to ensure that they are booting the correct software stack, such as cryptographic signatures over the BIOS, bootloaders, kernel, and base operating system image. The layer's fine features premises security. The layer's final feature is premises security. Good designs and builds its own data center. Google designs and builds its own data center. which incorporate multiple layers of physical security protections. Access to these data centers is limited to only a very small amount of Google employees. Google additionally hosts some server in third-party data center, where we ensure that these are Google-controlled physical security measures on top of the security layer provided by data center operators. Next is the service deployment layer, where the key feature is encryption of inter-service communication. Google infrastructure provides cryptographic privacy and integrity for remote procedure call. Remote procedure call. RPC stands for Remote Procedure Call. Data on the network. Google services communicate with each other using RPC calls. Repeat this. Google's infrastructure provide cryptographic privacy and integrity. Google's infrastructure provides cryptographic privacy and integrity for remote procedure call data on the network. Google services communicate with each other using RPC calls. The infrastructure automatically encrypts all infrastructure RPC traffic that goes between data center. Google has started to deploy hardware cryptographic accelerators that will allow it to extend its default encryptions to all infrastructure RPC traffic inside Google data center. Then we have the user identity layer. Google Central Identity Service, which usually manifests to end user as the Google login page, goes beyond asking for a simple username and password. The service also intelligently challenges users for additional information based on risk factors such as whether they have a login from the same device or a similar location in the past. Users can also employ secondary factors when signing in, including devices based on the Universal Second Factor open standard. On the storage service layer, we find encryption at rest security feature. Most applications at Google access physical storage, in other words, file storage, indirectly via storage services, and encryption using centrally managed key is applied at the layer of these storage services. Google also enables hardware encryption support in hard drive and SSDs. The next layer up is Internet communication layer, and this comprises two key security features. Google services that are being made available on the Internet register themselves with an infrastructure service called the Google Front End, which ensures that all TSL connections are being ended using public-private key pair and the X.509 certificate from a certified authority, as well as following best practice such as supporting perfect forward secrecy. The GFE additionally apply protections against denial of service attack. Also provide the denial of service protection. The sheer scale of its infrastructure enables Google to simply absorb many DOS attacks. Google also have multi-tier DOS protection that further reduce the risk of any DOS impact on the service running behind the GFE, Google Front End. final layer is Google's operational security layer, which provides 4 key features. First is intrusion detection. Rules and machine intelligence give Google's operational security team warnings of possible incident. Google conducts red team exercises to measure and improve its effectiveness of its detection and response mechanisms. Next is reducing insider risk. Google aggressively limits and actively monitors the activity of employees who have been granted administrative access to the infrastructure than their employee U2F use. To guard against phishing attack against Google employee accounts require use of U2F compatible security keys. Finally, there are stringent software development practices. Google employs central source control and requires two-party review of new code. Google also provides its developers library that prevent them from introducing certain classes of security bugs. Additionally, Google runs a vulnerability rewards program where we pay anyone who is able to discover and inform us of bugs in our infrastructure and application. You can learn more about technical infrastructure security at cloud.google.com/security/security design. Okay. Some organizations are afraid to bring their workloads to the cloud because they're afraid they'll get locked into a particular vendor. However, if for any reason a customer decides that Google is no longer the best provider for their needs, we provide them with the ability to run their application elsewhere. Google publishes key elements of technology using open source licenses to create ecosystems that provide customers with options other than Google. For example, TensorFlow, an open source software library for machine learning developed inside Google, is at the heart of a strong open source ecosystem. Google provides interoperability at multiple layers of the stack. Kubernetes and Google Kubernetes Engine give customers the ability to mix and match microservices running across different clouds, while Google Cloud Observability lets customers monitor workload across multiple cloud providers. Let's take a brief look at Google Cloud's pricing structure. Google was the first major cloud provider to deliver per-second billing for its infrastructure as a service compute offering, Compute Engine. In addition, per-second billing is now also offered for user of Google Kubernetes Engine, our container infrastructure as a service. Dataproc, which is equivalent of the big data system Hadoop, but operating as a service, and App Engine Flexible Environment VMs. Compute Engine offers automatically applied sustained use discounts, which automatically discount that you get for running a virtual machine instance for a significant portion of the billing month. Specifically, when you run an instance for more than 25% of the month, Compute Engine automatically gives you a discount for every incremental minute you use for that instance. Custom virtual machine type allow Compute Engine virtual machine to be fine-tuned with optimal amounts of vCPU and memory for the application so that you can tailor your pricing for your workloads. Our online pricing calculator can help estimate your cost. Visit cloud.google.com/products/calculator to try it out. Now, you're probably thinking, how can I make sure I don't accidentally run up a big Google Cloud bill? You can define budget at the billing account level and at the project level. A budget can be fixed limit, or it can be tied to another metrics. For example, percentage of previous month spent. To be notified when costs approach your budget limit, you can create an alert. For example, when a budget limit of $20,000 and an alert is set at 90%, you'll receive notification alerts when your expenses reach $18,000. Alerts are generally set at 50, 90, 100%, but can also be customized. Reports is a visual tool in the Google Cloud Console that allows you to monitor expenditure based on the project or service. Finally, Google Cloud also implements quota, which are designed to prevent overconsumption of resources because of an error or a malicious attack, protecting both account owners and the Google Cloud community as a whole. There are two types of quotas: rate quotas and allocation quotas. Both are applied at the project level. Rate quotas reset after a specific time. For example, by default, the GKE service implements a quota of 3,000 calls to its API from each Google Cloud project every 100 seconds. After that 100 seconds, the limit is reset. Allocation quotas govern the number of resources you can have in your project. For example, by default, each Google Cloud project has a quota allowing it no more than 15 virtual private cloud networks. Although projects will start at the same quotas, you can change some of them by requesting an increase from Google Cloud support. Okay. Now we have the quiz. Passing score 66%. What is the primary benefit to a Google Cloud customer of using resources in server zone within the region? Primary benefit of Google Cloud customer using resources in different zone within a region for better performance. Why might a Google Cloud customer use resources in several regions around the world? To bring their application closer to users around the world and for improved fault tolerance. What type of cloud computing service lets you bind your application code to the library that gives access to infrastructure your application needs? What type of cloud computing service lets you bind your application code to library software as service? What? What primary? Server zone in the region. primary benefit of Google Cloud customer of using resources in several zones in the region. In several regions around the world. Bind your application code to library that give access to infrastructure application need. It's a platform as a service. Okay, so I do have to read up this more. I do have to read the difference between infrastructure as a service, software as a service, and platform as a service. This one I understand, but this one as well, I thought is for better performance when you have different resources, different zone in the region. I mean, it's both for improved fault tolerance, like failover, and it's for better performance. Okay, this one is more primary than this one, than better performance. Okay.